Okay, so let's take a look at some more complex circuits here. And I'm looking at this first circuit, and you see we've got parallels, branches that have parallels within them, and then some series across those. And it looks pretty complex when we first look at it, but look at the way current's flowing. We're getting a path through here and a path through here, and only one path here and one down here. So if we cover up this part of it, we know what to do here. We solve this parallel, or if we were to cover up this middle part, we know what we do. We'd solve this parallel. So that's really all we're going to be doing here is getting rid of our parallels first. And you can see our current flow here is 35.2 milliamps. And we're going to notice that all the way through as we solve this circuit down. So the first thing that I did, doesn't matter if I start on this side or this side, is I solved the the branches within the branch, because this is one parallel branch, this is another, and then we have parallel branches within each of those. So let's do the 2 and the 6. So I took 2 times 6, which is 12, divided it by 8, and I came up with 1.5K. So this 1.5K right here represents what was this parallel branch. And notice I still have the 1K in series right here. So here I had a 3K and a 6K in parallel. So 3 times 6 is 18, 3 plus 6 is 9, 18 divided by 9 is 2K. So solve this branch, here's its equivalent. Solve this branch, here's its equivalent. Now, this branch that has both of these resistors is in parallel with this branch that has both these series resistors, but they're in series. So I'm going to have to add these two. So 1.5 and 1 is 2.5. Going to add these two, 1K and 2K is 3K. And now I'm down to just a simple parallel branch. So I'll break out the calculator for this because even using product over sum, that's going to be a little bit of a bear. 2.5 times 3 is 7.5. I can do that in my head. Divided by 2.5 plus 3 would be 5.5 equals 1.3636. And that's what I put in here, but it rounded it to 1.4. But if you look, our current 35.2 milliamps, 35.2 milliamps, 35.2, and 35.201, that's pretty negligible when you get down to the difference. So we've come up with the exact values for each of these. And now it's just a matter of plugging in some numbers and solving this circuit. So here's what we know. Our total current is 35.2 milliamps. Now I can come down here. I'm going to hit my escape key. And nope, I don't want to move that. I wanted to shorten it down. There we go. And I want to do the same thing over here because I want to show you this is why building these or solving these circuits down is very helpful. I'm going to add an ammeter here, and I'm going to add one here, and we're back to our 35.2, and we can see 19.2 and 16 here. Well, we know this is 48 volts. I didn't rewrite it at each source, but we can take and say 48 divided by 2.5K. We know our answers will be in millis, 19.2 milliamps. There it is. We can take 48 and divide it by 3K. Answers, whoops, I obviously multiplied. 48 divided by 3 equals 16 milliamps. We can add those two together and we got total current. So we know 19.2 milliamps is going through this branch and 16 milliamps is going through this branch. We also know that here. Now I could add in the ammeters and show you that. And in fact, let's do that just so you see it. Whoops, I didn't mean it. Forgot to hit escape. So let's drop these guys down. Whoa, didn't mean to do that either. A little tricky when you're trying to hurry. You know what? That current is right in the middle. Let's put it right in the middle of each one of them. That matter current is the same in any series, and for some reason it doesn't want to break that away. Here we go. So draw, let's do an ammeter. 19.2 and 6 milliamps. So now we've got how much current's going through this branch and how much is going through this branch. We can get the voltage drops of each of these guys. So I can come up here and I can say 19.2. Now that's in millis. Millis is 10 to the negative 3. K is 10 to the positive 3. So the good thing is they're going to offset each other. So I'm going to use base units. 1.5 equals 28.8 is how much this guy is dropping. So we did that calculation and got 28.8. Now it's pretty easy on this next one because it's 19.2 milliamps times 1. I can do that in my head. 19.2. I can't draw very well, but I can math in my head. So 19.2 plus 28.8 gives us 48 volts, which is what that branch is dropping. Over here, I can do this math pretty easily. 16 times 1 is 16, and these are volts, although I just don't have room to write. And 16 times 2 is 32 volts, and that adds up to 48. So no surprise there either. So basically over here, we've got 48 volts across the branches that run this way. But we've got parallels within those, so how do we solve those is the question. So let's take a look at that real quick. So we know we've got not our 16 milliamps coming through here, and then that's going to split off. Now we could put the current in here, or we could look over here and say, oh, got 16 volts right there. We know that because this 1K and that 1K are the same thing. Well, if we got 48, that means we got 32 volts right here. So we could divide that 32 volts that we have by 3 and then by 6. So 32 divided by 3 equals 10.6 milliamps of current coming through that 3K. It's going to be hard for me to write, so I'm just going to kind of point to it. So we'll say 10.6 milliamps right there. And we'll come out here and do the same thing. Actually, I should point that way, hadn't I? And we'll do that math real quick. So we'll take 32 and divide it by 6. And that is 5.3 milliamps. 5.33 milliamps right there. And if we add 10.6 and 5.3, no surprise, we get close to 16. We got a little bit of a rounding issue, but no biggie, very close. We can do the same thing over here. We know we've got 19.2 milliamps. We're dropping 19.2 volts here. So we've got 28.8 volts across this branch. So we can come over here and we can take, say, 28. Actually, I can do that in my head. 0.8 divided by 2. And that is not right. 28.8 divided by 2 equals 14.4. 28 divided by 2, yeah, 14.4 milliamps. That's right. So I'm going to try to write that for us. I'll try to sneak it in here. 14.4 milliamps. And I know my writing is horrible, but it's okay. And we're going to come over here and do 28.8 divided by 6. And that gives us 0.583 milliamps. And obviously, if I add 14.4 plus 14.4, 14.4 equals 14.98 milliamps, which doesn't add up. So what have I done wrong here? Obviously I've done something wrong. So let me come back. I know this is right. 28.8 divided by 2 is 14.4 all day long. I think I screwed up when I did it by 6. 28.8 divided by 6. Yeah, that's 4.8. So let me write 4.8 there. I definitely had a fat finger or a fat mouse error on the so 14.4 plus 4.8. Let's add those two together. 14.4 equals 19.2, which is what we had. So all is good there. So it's just a matter of working through these circuits and understanding how to solve them. So again, to recap a little bit, I'll draw a little bit and I'll use a different color other than green. But obviously this is a parallel branch that has parallel branches in it. This is a parallel branch that has parallel branches in it. So what we needed to do was solve this parallel branch, put it back in series with this 1K that's right here. Then we solved this parallel branch, put it in series with the 1K that was above it. We added these two together, just basically said 1.5K plus 1K, 1K plus 2K, and we came up with 2.5K here and 3K here. We solved that parallel branch and we just started working backwards. We started realizing the things we understood. We could get the current through this branch and the current through this branch, which is the same current that runs through these equivalents, which is the same current that runs totally through this one, and splits between these two here for that branch and these two here for this branch. So it's just a matter of understanding what we've got in front of us, applying those things, and making sure we dot our I's and cross our T's and don't mess up on the calculator. And Ohm's law once again proves itself. But as always, if you have questions, please let us know.